where U is a nonlinear mapping. So we have seen these two problems. Okay, so the next thing to do is to check what they actually did, because it's a published paper. So an abstract will give us a direction to what was done in the paper. So again, the paper is about some extragradient viscosity algorithms for solving relational inequality problems and fixed point problems. So in repeat, I said that means what they are trying to do here is to find a common solution to two problems. That is, they are seeking a point in the intersection of two convex sets. So the first set is a solution to the relational equality problem, and the second set is a solution to the fixed point problems. Do you understand?
Yes, yes.
Okay. So that's from what I've mentioned, we can also describe or give another title to this paper. So here we can say a convergence method for approximating a common solution to relational equality problem and fixed point problems. That's another method of saying it. So instead of mentioning the method, here they've mentioned the method that they use, that is extragradient viscosity. So I can say an algorithm for approximating a common solution, or some algorithms. I've not even mentioned the type of algorithm. I only say it's an algorithm or it's some algorithms for solving that. So now, like I said, we go through the abstract. I said the purpose of this paper is to study and analyze two different kinds of viscosity type IGT methods for finding, you see this now, you mentioned it, a common element, of the set of solutions of the relational equality problem. Now they mentioned the type of function that the relational equality problem is. That's the monotone function. And another property of that function is that it's Lipschitz continuous. And the set of fixed points of what type of mapping? Mapping. So what type of mapping for the relational equality problem? A monotone and Lipschitz continuous mapping. Okay, so this, we can, another way of improving on this method, or on this paper rather, is to change this mapping. Now this mapping is monotone, right? So we can weaken the condition of this monotonicity to make it pseudo-monotone, and instead of it being Lipschitz continuous, we can make it uniformly continuous. So if we do that, we're generating another result entirely. So it's going to be a new result, because the relational equality problem is no more associated with a monotone operator, but a pseudo-monotone and uniformly continuous. That's one way of improving. Another thing is the set of fixed points. That this demi-contractive mapping is contained in another bigger mapping, which is the demi-metric. So instead of having a solving fixed point for demi-contractive, we can change it to demi-metric. So that's another thing. They said, although the problem can be translated to a common fixed point problem. You see what I've said the other time. I said we are looking for a common solution in the intersection of two convex sets. They said, although the problem can be translated to a common fixed point problem. Do you know why? Because the last time we mentioned that solving the relational equality problem can also be recast as a problem of finding a fixed point. Do you remember that statement that time?
Yes,
Yes, sir.
I would say it's like solving x star equals PC of I minus lambda A of x star. So now, if we can recast the relational equality problem, if we can recast this as a fixed point problem, so it means we have two fixed point problems. This is one fixed point, this is one fixed point. So we are looking for a common element or a common solution to two fixed point problems. But now look at what they have said. They said, although the problem can be translated to a common fixed point problem, the algorithm structure is not derived from algorithms in this field, but from the field of relational inequalities, and hence can be computed quite easily. They said we extend several results in the literature from weak to strong convergence in real Hilbert spaces, and moreover, the prior knowledge of the Lipschitz constant of cost operator is not needed, which means they have either used a line search technique or a self-adaptive technique. So if they are not
Method.
in need of the Lipschitz constant, it means they have used one of those two things. Either it is line search or it is some self-adaptive. So, but let's see which one they have used. So we proved two strong convergence theorems for the sequences generated by these new methods. Primary numerical examples illustrate the validity and potential applicability of the proposed schemes. Okay, so this is the problem. This is the VIP. And they've mentioned that the simplest projection method for this is in which only one is performed. So that's this story we're already used to that story. You may want to go through again to brush up what we've learned. And this is the subgradient extragradient method. Here, this is what they call the subgradient extragradient method. If you remember this, so it's one projection onto the physical set and a projection into the half space. So this is the half space here. So this combination is a subgradient extragradient method, and this was what we did in the last one. So the Seng extragradient method. Why is it extragradient? Because the A appears twice in the sequence.
Yes,
this is one A, this is one A. So also here is also extragradient because this is in the first line here, first step, there's A here. In the second step as well, there's A. So that's why it's extragradient. Okay, so they said this Seng extragradient method and subgradient method need only to compute one projection to the VI's feasible set by iteration. So you see, it's just one projection to the feasible set. This is PC, just one PC here, just one PC here. Here, PTN, that's a projection into our space. And there's a formula for this. There's a formula. So this one is easy. We can use the formula of this guy. Instead of writing it this way, we can just use the formula. It has a formula. So a projection onto this is as a formula. So that. Then this is also the fixed point problem. You also recall that the fixed point problem. And jointly what they are trying to do now, you see, we are finding a point in the intersection of two convex sets. You can see this is the first convex set, which is the set of fixed points of the operator U, and the solution of the VIP. Do you understand?
Yes, sir.
Yes.
Okay. A minute, please. I want to check on the other person why is he not here. About who else is available or who is here? Okay, now Dr. Gafaro Tilo. Yeah, he's still there. So, okay. Yeah, Dr. Gafaro has entered now.
No, only
Dr. Musa,
See Dr. Musa Niesha.
Shawani.
Yo, Ekalesa.
Okay,
Familiar with
Shawani.
Dr. Abdul Gafar.
Okay.
Ekabo. So that is this is the formulation of the problem they want to consider now. So, and you remember here in this paper, they said U is demi-contractive and A is monotone and Lipschitz continuous. But I just mentioned that we can improve on this by making sure that the U is not only demi-contractive, but a bigger mapping. For instance, the demi-metric. So we can replace this demi-contractive by demi-metric and replace this A, which is monotone and Lipschitz continuous, by a pseudo-monotone and uniformly continuous. So we can make it pseudo-monotone and uniformly continuous. As well, we can make it quasi-monotone and uniformly continuous. So those are weaker operator than the monotone that they have studied here. So, but I want to believe somebody has done that already. So we may not go through that. Maybe somebody has done that. I want to think someone has done that. Because I can still remember I did something like that. I'll study this problem too, where I think you use the mean metric, and I think A is the monotone. If I'm not mistaken, I've studied it before myself. So this same problem, that is finding a common. Okay. So this same problem now. Okay. So that's another thing. That's another way. He has used Seng to solve this same problem, but here they are using the subgradient extragradient. So if you go to the algorithm, it is subgradient extragradient.
Okay, sir.
So this is one of their methods. So this first one is subgradient, extragradient,
Yes, sir.
combined with what? With viscosity
With
and
viscosity.
man.
Yeah.
So this
Yeah.
this is man, this is viscosity, and here is the subgradient, extragradient. So here is where the variational inequality is solved, and here is where the fixed point is solved. You can see the two problems now. So the
Yes, sir.
variational inequality is solved here. You know, the
At
the
yn.
solution to variational equality will be obtained when yn equals xn. When yn equals xn, we're going to have the variational equality. You know, because if you put xn here, tell about the xn, also can see that fixed point formulation to Montreal facility. So we just so
Then
it means when xn equals yn, we arrive at the solution of the fixed point of the variational equality.
variational
And
equality.
here, when uzn equals zn, we arrive at the fixed point of u. When uzn equals zn, we arrive at the fixed point of u. Please take
Yes, sir.
note of what I just mentioned. When
Yeah.
uzn equals zn, we have arrived at the what? The
At
fixed point of
fixed
u.
point of view.
And
It's like
when
u of
yn
equals to
equals xn, we have arrived at the solution of the variational equality. Okay, so
Yes, sir.
which means what that means is, in essence, is that you must obtain the limit of yn minus xn. You have
Yes,
to
sir.
show that the limit of yn minus xn as n goes to infinity equals 0. Also, that the limit of uzn minus zn as n tends to infinity has to tend to 0. That's what it means. Those two limits are very, very essential. That's two.
Okay.
The third one is that you have to prove that the sequence is asymptotic. What does that mean?
We
That
have to show
sequence is
that
asymptotic mean
Sn plus 1 minus x. Limit of Sn plus 1 minus x tends to infinity. I mean, goes to infinity, it tends to 0.
nonsense. That's not correct.
Ah.
To show that the sequence is asymptotic implies that the norm of xn plus 1 minus xn goes to 0 as n goes to infinity. That's what it means. It's not xn plus 1 minus x. That's wrong.
Sn no mo pe, Sn mo pe.
The video will be out. You listen to it
Yeah.
again. The norm of xn plus 1 minus xn tends to 0 as n tends to infinity, shows that the sequence is asymptotic. So those are three very, very important limits that you have to obtain.
Right.
Those are the very, very three. So, but sometimes you have to obtain more to be able to get those three. But
Yes,
the
sir.
most important thing, the most important limits that you have to establish are those three that I've mentioned. So, but sometimes it takes you more to get those three. You have to do more, find more limits to be able to do that, and you use your triangular inequality to get whatever missing stuff. So, like I said, or like I used to say, whoever is using the same method, that is, whoever is using this subgradient, extragradient, so whatever they have gotten, if you're using the same method, you have to get the same thing. Like this lemma 3.8 now, this lemma 3.8, that is Zn minus p squared. If you're using the same method to solve whichever, whether it is monotone, whether it is pseudo-monotone, whether it is quasi-monotone, you must obtain this inequality here, 26. You have to obtain it. So that inequality, you have to obtain it. So how did they obtain this? I don't know if we have to go, if we must go through them one by one, but this is exactly what we've seen before. So only that, just if you have any question, you can ask here. So this, we have seen something like this, though the one we saw then was for Seng. You remember?
Yes, it's almost the same thing.
Yeah, it looks almost the same thing. So, but whatever they have used, that's what we have to find out. Here, what did they use here? So they use one of the identity in a different way. The identity they used here, they used one of the identities in a very different way. So what way was it? What way was this? So they used one of the identities in a very different way. They use one of the identities in a very different way. So what is that identity? Is that identity of x plus y squared, norm of x plus y squared equals norm of x squared plus 2 into inner product of x comma y plus norm of y squared. So
Yes, sir.
that's what they have used here.
Hello, sir.
Yes.
Yeah, from the beginning, sir. Zm, norm of Zm minus p square equals PTN. Yeah. Well, pé PTN half space yìí by minus p rẹ kó jẹ́. So kí ni lemma tó gbélé wá PTNP yìí? How come
PTNP.
tí PTN fi attachment p mi báyìí? Why tó jẹ́ p nìkan?
Okay. Ṣé ẹnìkankan máa answer?
Wọ́n ti describe, wọ́n ti fún wa ní definition níbi ṣó lọ síbi òkè yẹn náà níbi tá wọ́n ti fún wa ní definition Zn minus p1 become to be PTN or something.
Yeah, that nǹkan tó sọ náà ni Zn lélẹ̀.
Yes.
But the question now is, this was P. It should be minus P, right? But it's now PTNP.
Okay.
That's what he's saying.
Mo pé lemma kan ló máa sọ di báyìí sir, but I'm not. I don't. Wọ́n dẹ̀ indicate ní lemma rẹ̀ síbẹ̀ sir.
Kò ṣe lemma. Okay, ṣe lemma.
Okay, sir.
So think about it.
So what did they use?
Àbí ṣé tó bá ti jẹ́ half space báyìí ṣé bá ṣe máa ṣe nìyẹn?
Stop guessing.
Okay, sir.
Yeah, but I'm square more.
Mo náà
I'm
ní.
going to show more smart
Mo rí inú
power.
pépà yín kan náà báyìí so.
What is PTN?
PTN is half space.
Ìsọkúsọ nìyẹn, kò ń ṣe half space.
PTN projection.
PTN is a projection onto the half space.
Projection of half space.
Kí ni projection? Kí ni projection gangan?
It's a mapping.
Rúru mapping wo? Mo ti sọ́rí.
Irú mapping wo? Ṣé
Projection is what they call the nearest point mapping. The nearest point mapping.
Okay.
Projection is what they call the nearest point mapping. So which means pé kí ni is P not equal, ṣé tá bá sọ pé P, for instance, say P bá wà ní the same set yẹn. Point wo ló fẹ́ tún near sí P ju P lọ? Ṣá lè rí point kan tó lè near sí P ju P gangan fúnra lára ẹ̀ lọ?
No, sir.
No.
Kò sí. So which means pé P itself is also projection of Tn onto P. It's the same thing. So P will always be the fixed point of the projection mapping. You know, get any point will always be the fixed point of the projection mapping. If it is PC, I can say X is the same thing as PC of X, because kò sí element tó tún lè súnmọ́ element kan àyàfẹ́ element yẹn fúnra lára rẹ̀. Kò sí element tó lè súnmọ́ jù. For instance, Zn rèé, Zn ten way is the projection of this point here, xn minus this thing, onto this set Tn.
Yes, sir.
Projection eléyìí ni. So eléyìí sìn, a lè pe the whole of this thing as P again because kò sí the nearest point tó wá sí tó súnmọ́ P sí P tó súnmọ́ P kò sí nínú element tó máa wà ní Tn ju P gan fúnra lára ẹ̀ lọ. Mi ò rọrùn ẹ̀yìn yé bí mo ṣe ń sọ yẹn.
Yes,
Kò sí
yes.
element tó fẹ́ súnmọ́ ju P fúnra lára ẹ̀ lọ. That's why we say P equals the projection of Tn onto P. So instead of writing it as P, I can write it as P Tn of P. So I can write it that way. So
Okay.
now, how is it less than or equal to this guy? Kí lorúkọ ẹ̀ wà ń bẹ̀? Báwo lè lè ṣe wà less than ilé? Ó wà lára àwọn property kí lorúkọ ẹ̀? Ó wà lára àwọn property firmly non-expansive mapping. PTN is firmly non-expansive. And this is the definition. When something is firmly non-expansive, the definition lele. Let's go to the lemma. You recall this is what it means. The reason that I fẹ́ so we want to use the property that PTN is firmly non-expansive. We're not arrive at this guy. So this the first question is clear, right? Billy Sije, Abi?
Yes,
Yeah,
sir.
Now, balance was less than a they have used the property that PTN is what? Firmly non-expansive. Firmly non-expansive. So I want to take you there. What is the definition of firmly non-expansive?
Awesome.
Oh, my defines. Okay, only. So PCX minus PCY all squared is less than or equal to PCX minus PCY, comma, X minus Y. Can you see that? PCX minus PCY, comma, X minus Y. Take note. Into one in square.
Shall share paper again?
Kẹ́yìn náà máa wò lọ́dọ̀ yín fúnra lára yín. Ṣé ẹ rí báyìí?
Pé orí fóònù tí ń wò sọ̀rọ̀ tó ń bá go through after this start máa lè.
Okay. FPP and VIP. Mo ní máa ti ṣe yín báyìí.
Ẹgbẹ́ sí group báyìí.
Okay. So. Try láti ṣe bí ẹ ṣe ń sọ yẹn náà ni. Okay, so let's go back. Now, let's property. So PCX minus PCY squared is less than or equal to PCX minus PCY, comma, Kinan project C, X and Y, X minus Y. Now let's go back. So where it was used. So we have PTN of this guy minus PTNP. So the whole of this thing, ZN.
Then
Minus PTNP, see the same thing as what? P, comma, Kinan project C, this guy, minus P.
Okay, yeah.
So it's clear?
Was it clear, sir?
Clear.
Now, on va sọ pé this is equal to this guy. So mo try láti sọ nǹkan lò tán fi get ilé what is that? Identity that were used, so they use it in a different way. So where is identity? Okay, look at this identity tán lónìí. Ṣàpọ̀ wọ́n bẹ̀rẹ̀ pẹ̀lú kí lórúkọ ẹ̀? Wọ́n bẹ̀rẹ̀ pẹ̀lú inner product.
Yes, sir.
So tẹ́ bá kọ inner product only minus náà lò kò ṣe ní plus. So just change this to minus, change this to minus. Try and get by. Change this to minus, change this to minus. This eléyìí àti eléyìí nìkan lè change to minus. Ẹ wá gbélé lọ sí the other side. Tẹ́ bá ti gbé lọ sí the other side, ó máa kú eléyìí, then eléyìí máa wá di minus níbí báyìí. Àbí?
Yes.
Yes,
You now divide everything by 2.
Okay.
Unless you read gbogbo ẹ̀ ní 1/2, 1/2 tẹ̀ ń wò yẹn. So the inner product will be equal to this guy. So tẹ́ bá ṣe pẹ̀lú minus bí mo ṣe sọ yẹn. So bẹ́ẹ̀ máa get bí báyìí nìyẹn. And if you look at it now, this first step, eléyìí, ó repeat ara ẹ̀, àbí?
Yes,
Yes.
sir.
So that step has been used here again. Uncle as x lọ́tọ̀ minus this guy. Gbélé wa replace eléyìí, gbélé sí bí báyìí. So wá lo kíní again láti fi get eléyìí. So that you should be able to find out the rest after this one. So then they said this implies this guy that this one gbélé wa bá bí báyìí. So then you multiply everything by 2 again to give this. So clear, right?
Yes.
So you should be able to find this out. So that one, this shouldn't be a problem. So Tebatin, if you run into anything, you can let me know. So this was before another way that if you continue. So every other thing here, you should have seen them. So, and I think this work as well, since you're putting on the viscosity, all right, put our treat a lot of viscosity, Navi.
Yes, sir.
Yes.
So which means the same thing that I get from Kiniwa. Banded kí ló ń pè pó wà banded yẹn, we're going to arrive that this thing is banded. Well, we not prove bandedness. We check about this. Nínú tá a ti ṣe tẹ́lẹ̀ náà lè máa bá ń bí báyìí. So it's still that we're going to see here. So I'm not going to run into any problem trying to show that it's banded. So the only thing to change instead if you just sang, so it's now subgradient, extragradient, and I've already shown you what we're going to achieve. They are very, very simple things. So but why am I bringing this up? Lately, they are improving these methods. And improve our method. One, method time we currently cooking say inertia. Are you with me?
Oh, yes, sir.
Yes.
So one way that if you improve method apart from we can improve problem, in what sense? I change the map map to 1B is monotone and it is continuous. Map to 1B is demi-contractive. And so another way of improving this is by we can weak this operator. Instead of it being monotone and Lipschitz continuous. And so quasi monotone. Quasi monotone. Yeah. So one way here. Then Elaine and change it from demi-contractive to demi-metric. So at a weekend kini. Okay. Another thing ni method you go from alare. Ali find the same problem. This same problem that only solve, but can improve method here. But inertia. That's one way. Another thing is I improve by golden ratio. That's another way. Another thing is of recent now combination méjèèjì yẹn ti ń wà golden ratio and inertia tàbí kó jẹ́ double inertia. So ìyẹn gangan mo fẹ́ ká look towards now because mo sọ ní last week pé it's almost time I give you a project to máa jẹ́ joint project everyone.
Yes, sir.
Okay.
So this same work here, I'm a paper on the double inertia fún. So we now add double inertia to this. So I'm a kọ́kọ́ bẹ̀rẹ̀ pẹ̀lú ẹ̀. Tá bá find out wọ́n ti ṣe the same thing. We are the same operator, wọ́n ti ṣe pẹ̀lú double inertia tá fẹ́ lò yẹn. Then we change it again to something else. At least let's have an output from this class already. Clear.
It's clear.
So we are at the point where we should be able to try out something. So let's try and work out something, even if it is joint paper that will not include me. So let's see what we can achieve. This is a method now that's been used for variational equality problem and fixed point problem, right? The variational equality is associated with what operator, monotone, and which is continuous. The fixed point problem was for what?
Was for
A demi-contractive.
contractive.
So you recall, what are the limits tí mo sọ pé a ní láti generate láti get solution wa? The three most important limits that has to be established
You
here
have
is
to
what?
find the limit of 1n minus xn goes to infinity at x tends to
as I go to 0 as x tends to
infinity. It goes to
Yes, sir.
0 as n tends to infinity. Calm down, Soro. Do not rush it.
Sorry, sir.
Yn minus xn goes to 0 as n goes to infinity, the norm of that. Secondly, is that what? The
We have
distance
to find
between
the
uzn
limit of
minus
uzn minus
zn
zn.
is 0 as n increases. The distance between uzn and zn is 0 as n increases to infinity. And finally, we have to show that the sequence is asymptotic. What does that mean? That is xn plus 1 minus xn goes to 0 as n goes to infinity. Okay?
Yes,
So those
sir.
are the three most important limits. Now let's check the limits they established here. Let's see. The first one. Can you see this first one?
Yes.
Yes, sir.
Yes.
xn minus
So
1n.
this is for the VIP. See the second one again. That's the meeting also.
That's
Yes.
6 points.
This is for the fixed point. Now, this is another limit. Kí lẹ ṣe rò pọ́n fẹ́, kí ló dé tán ṣe need láti establish limit eléyìí?
Because
Kò sí nǹkan kan tán fẹ́ fi establish ẹ̀ ju pé wọ́n ní ìdẹ̀ níbi asymptoticity tá a fẹ́ wá yẹn. Ó wà
Okay.
required ń bẹ̀. And next we show that ẹ ti rí báyìí sí wọn. Gbogbo àwọn eléyìí tán show yìí. One, this is the first one, kò ní meaning. This is the second one, kò ní meaning. This is so gbogbo àwọn eléyìí ó kàn fẹ́ ràn wọ́n lọ́wọ́ láti fi get kí ni o, ó wà asymptotic. Ṣé ẹ pé three important láti dárúkọ, àti rí alákọ̀ọ́kọ́, àti rí alákọ̀ọ́kọ́,
Bẹ́ẹ̀ sà.
àti rí ẹlẹ́ẹ̀kejì, àbí?
Bẹ́ẹ̀ sà.
Yes.
So gbogbo tó bá tún ṣe yìí, tó gbogbo tẹ́ bá rí níwájú yìí, wọ́n fẹ́ fi get the last one ni, wọ́n fẹ́ fi get ẹlẹ́ẹ̀kẹta ni. Because àwọn eléyìí ò ní meaning kankan sí wa. Sí nǹkan wúlò fún. Èyí tó wúlò ń bẹ nǹkan mẹ́ta péré ló wúlò. Eléyìí wúlò, eléyìí wúlò, àti pé ó wà asymptotic. A dẹ̀ ti rí méjì nínú tó wúlò. Gbogbo eléyìí tán ṣe yìí kò sí ní tó wúlò. So which means pé wọ́n ní ìdẹ láti fi get kí ni o, ní tó wúlò yẹn. Ṣé ẹ ti rí sìn? Nígbà tán fẹ́ prove ẹ̀. Òrìn eléyìí sìn, eléyìí clear ṣé wọn bí lè ṣe lọ sí 0. Kí ló máa lè lọ sí àti sọ tẹ́lẹ̀ already o. Ní tó lè mú eléyìí lọ sí 0 is the alpha n.
Alpha n.
Yeah. Now, wọ́n ní the zn minus xn. Wọ́n dẹ̀ ní tn minus zn. Ṣé ẹ ti rí báyìí?
Yes, sir.
Òrìn.
It
Then
has been gotten.
zn minus xn náà. Òrìn.
Yes, sir.
Wọ́n ní ìdí wọn láti fi establish pé wà asymptotic náà ṣe prove, otherwise àwọn gangan kọ́ ló wà important. So ti yé báyẹn?
Yes.
Nínú Islam, nǹkan tó bá jẹ́ ọ̀ràn yẹn, intense débi tó fi jọ́ràn yẹn náà ọ̀ràn yẹn ló náà. Lórúkọ afẹ́ lọ kírun sí irun ọ̀ràn yẹn nínú. So a dẹ̀ gbọ́dọ̀ ṣàlùwàlá ká tó kírun. So ó túmọ̀ sí pé àlùwàlá náà ń kọ́ ọ̀ràn yẹn ló náà máa jẹ́. So torí wípé a lọ sí xn plus 1 minus xn tó jẹ́ important, ó mì pé àwọn eléyìí náà tá a lò láfi débẹ̀ náà jẹ́ pàwọn náà ṣe kí ni o, ọ̀nà wà important ni. Because tán àbá rí wọn, a lè rí eléyìí. So ti yé?
No.
Yeah.
So bọ́n ṣe wá prove pé bọ́n ṣe prove solution set ti variational inequality yẹn, bẹ́ẹ̀ náà ni wọ́n á ṣe prove ẹ̀ anywhere since tó ti jẹ́ pé monotone ni. Gbogbo paper tó bá ṣe monotone solution set bọ́n ṣe prove ẹ̀ bákan náà ni, kò sí yàtọ̀. Bákan náà wọ́n á ṣe prove ẹ̀. So kò sí yàtọ̀ rárá. But solution set fixed point báwo la ṣe ń prove ẹ̀? Ìyẹn náà step kan péré, 1 or 2 step only. By 37, we have that znk. Nígbà tá a sọ pé xn lọ sí, ó convert weekly sí kinní kan, tá a dẹ̀ ti sọ pé xn minus zn lọ sí 0 ó mi pé ibi tí xn bá converge sí zn náà gbọ́dọ̀ lọ bẹ̀ nìyẹn tó ti yé.
Yes. Yes.
So àwa lè lo 37 sin 37 yẹn ni uzn minus zn ẹ lọ yẹ̀wò o. No ilé ìkọ́ 35 ó yẹ kán pé méjèèjì papọ̀ ó yẹ kán pé orí eléyìí àti eléyìí zn minus xn yìí ló jẹ́ ká mọ̀ pé ibi tí xn bá lọ zn náà ti lọ bẹ̀ àbí.
Yes, sir.
Yes.
So mi pé eléyìí sì lè change sí znk yìí sì yẹ pé xnk lọ sí z then znk náà lọ sí z tí ló máa jẹ́ z minus uz equals what 0 àbí.
Yes, sir.
Z minus uz equals 0 tó yẹ pé z xnk ó convert weekly sí z ní o sóyè. So
Yes,
pé
sir.
z ní
Yes.
tẹ́lẹ̀ bá convert lọ sí xnk ó convert lọ sí z for instance so which means pé by since ọgbọ́n ti lọ 0 mi pé lẹ́yìn náà lọ sí z ní àbí.
Yes, sir.
So tó bá
Yes.
ti wá
Yes.
lọ sí z ní tó túmọ̀ sí pé z now minus uz equals 0 àbí.
Yes, sir.
Yes.
Which implies z equals uz.
Yes. Yes.
Yes, sir.
So tí z bá ti equals to uz kí ni ìtumọ̀ ẹ̀? Z is in the fixed point of u. Mo rò pé báyẹn.
Oh yeah.
Yes, sir. Yes, sir.
So ìyẹn náà ṣe arrive bí pé z is in the fixed point of u.
You. Wow.
So to get.
Yes, sir.
So ṣẹ̀ṣẹ̀ prove solution set ẹ̀ kàn lọ gbé lemma kan wà ní lemma tán ti fi prove ẹ̀ rí ó ní lemma 2.3 àwọn ò dára wọn láàmú àwọn èèyàn kan ti prove ẹ̀ rí so instead táwọn ti máa tún prove repeat the same thing tá a ti rí all over wọn kàn gbé lemma àbí tán ti prove ẹ̀ wá ní ṣẹ́rí báyìí
Yes, sir.
àkọ́ gbé lemma yẹn wá títí wọn ni so let's go to lemma 2.3 and see. ó ní lemma 2.3 rí. So let this monotone and ellipsis continuous mapping let S be ní terms ẹ ti rí pé bí mapping yẹn nìyẹn so where mu is this if A is a sequentially satisfied xn converge weakly to this and xn minus xn goes to 0 then Q is in the solution set of this which is
Set of VIP.
the fixed point of S. Yeah, so ìyẹn náà ló direct set táwọn tún ṣẹ̀ṣẹ̀ máa tún prove wọ́n ti wá lo lemma láti fi gbé solution set VIP wá. So ìyẹn fún gbogbo tó tán ṣe inú pépà yìí
Solution set
nìyẹn
VIP.
every you should be able to do
Yes,
it.
sir. Wọ́n tún wá show pé àgbẹ̀
Eh?
common solution. Mo ní solution set of VI yẹn wọ́n ní equal to fixed point. That means ṣé wọ́n ti show common
Since tó ẹ
solution?
pé ó ti wà nínú the same z ó ti wà níbí the same z ó ti wà níbí so mi pé ó wà nínú ìtumọ̀ ẹ̀ náà nìyẹn náà pé ó wà nínú intersection àwọn méjèèjì ṣé kò clear ni ìgbà
Ó
láti
ti yé
establish
láti
pé ó wà nínú civilization equality establish pé ó wà nínú fixed point so tó túmọ̀ sí pé ó wà nínú intersection àwọn méjèèjì nìyẹn
bẹ́ẹ̀
ṣé
sir.
ó clear
Ó clear sir.
doctor so clear.
Yes. So clear. So clear.
So nǹkan tó wà mẹ́rin yẹn so every other but the only thing now is now this one in this paper now lo àwọn approach tá a lò tẹ́lẹ̀ àwọn case two lo paper àti bí yẹn ṣe é pé NK
Network ń break.
Gbọ́ dáadáa.
Yeah, nǹkan tí mo sọ ń sìn ni pé manner of establishing the strong convergence nínú pépà eléyìí ó yàtọ̀ sí ti pépà talákọ̀ọ́kọ́ pépà talákọ̀ọ́kọ́
Okay.
yẹn
Okay.
àwọn ò lo case 1 case 2 báwọn ilé ṣe lóye case 1 case 2 òun láti máa ń lò tẹ́lẹ̀ mo mention nínú kíní pépà kíní tí mo ṣe ń gbà yẹn tí mo pè ní teaching that
Okay.
kíní tí mo kọ àwọn slide tí mo ṣe yẹn
Yes sir. Yes sir.
so method àti máa ń lò tẹ́lẹ̀ ní case 1 case 2 case 1 case 2 but tẹ bá wo paper àti bí yẹn kò ṣe case 1 case 2 and
Kí wá ní-
kò necessarily mean pé gbọ́dọ̀ lo case 1 case 2 so
Kí
let's
wá
not
lórúkọ
use
method
case
yẹn
1
lè?
case 2 ẹ jẹ́ ká lo method èwo ni ẹ
Ti bí yẹn.
ohun
Tí bá ṣe case 1 case 2 kí wá.
ibẹ̀ ṣe june lemma náà lò ń bẹ̀ kò kí n ṣe case 1 case 2 ṣe june lemma tí ó bá ti jẹ́ case 1 case 2 it's the same june lemma they have used
All right sir. All right.
this is the lemma they use. The moment you see this lemma, this is what I call the Sejun lemma. The moment you see this lemma in any paper, look, case 1, case 2 nìyẹn. Any paper, automatically lo lemma item
Oh,
we
láti
see
lo
kò ṣe case 1,
ANK
case
plus
2
1
nìyẹn lo.
equals to kìíní. Okay.
Automatically, this guy is greater than or equal to 0, then this. The moment the lemma is this guy, look, case 1, case 2. So
Okay, sir.
automatically lo lemma. So for strong convergence. But if this lemma has not been used, the same inequality náà ni o, inequality náà ló gbọ́dọ̀ satisfy fún èyí tó jẹ́ case 1, case 2. Let's go back. You see that it's still the same inequality. But the extra condition till it satisfy tán show bẹ́ẹ̀ ni ló fi yàtọ̀. Ẹ ti rí pé the same inequality ni.
Yes,
The
sir.
same inequality. But at the end of the day, when you proceed in that one, ẹ máa rí pé subsequence ti wà ńbẹ̀. Instead of combine ilé àti ilé papọ̀, ilé tó máa ti lo case 1, case 2, lẹ́ẹ̀ma méjèèjì tẹ̀ máa bá mẹ́rin. Ilé is always necessary. This is always there. Tó máa ti lo case 1, case 2, ẹ máa bá ilé ńbẹ̀ ṣáà ni kò sí. This one will always be there. But tí o bá ti ṣe ilé ńbẹ̀, tẹ̀ dẹ̀ rí subsequence iwájú, that is, ẹ rí nǹkan báyìí. Ẹ rí irú nǹkan báyìí. Ó mean pé kí náà lò yẹn o, Sejun lemma. So kò sí case 1, case 2 nìyẹn. Irú ẹ̀ ni omi náà prove strong convergence paper alákọ̀ọ́ta treat yẹn. So it's clear.
Yes.
So kí ni mo wá sọ ń sìn ni pé now what you're going to do now, I'll share this paper with you. Mo máa wá paper àti ṣe double inertia náà máa send ẹ̀ sí so that you understand what double inertia is all about. Double inertia. Okay, mi ò ti share yẹn, mo ti share ni. Now ẹ wo tán ṣe ń sìn double inertia pẹ̀lú kí ni o? Can you see?
The monitor
The
map.
monitor-
Monotone and
non-ellipsis.
non-ellipsis mapping.
Kò ń ṣe ilé ò kì í ṣe kí lórúkọ ẹ̀ kò ń ṣe common solution lẹ́yìn pé kò ń ṣe common solution, it's just for bidirectional equality but with what? Single projection method.
Yes, sir.
Ẹ já lọ wo projection yẹn ṣé seng ni àbí nípa kò lè jẹ́ kí lórúkọ ẹ̀ subgradient because projection kan péré náà ló wà ń bẹ̀.
Bẹ́ẹ̀ ni kò lè jẹ́ seng.
Ṣé à pé subgradient projection méjì ló wà ń bẹ̀?
Bẹ́ẹ̀ ni, sir.
Ìkan sí feasible set, ìkejì sí half space. So which means this will not be subgradient, but ó lè jẹ́ seng because nínú seng náà single projection ni. A fẹ́ send the paper méjèèjì. That's all. So the first paper. So I've added those two papers. Síbẹ̀. Now eléyìí sìn non-ellipsis náà pé so kìíní náà ló ń sìn line search instead of self-adaptive. Okay, so what type of method? This is a projection contraction. Method yìí náà pè ní projection contraction. Ẹ bá ti rúurú nǹkan báyìí. Method yìí ṣe dáadáa method láti ti ṣe láti ti wọ̀n sìn projection contraction. So instead of looking student, all right, kò dẹ̀ kí n ṣe seng. so àwa lè change ẹ̀ sí seng báyìí sìn tàbí ká lo no ẹ má jẹ́ ká lo subgradient a lè change ẹ̀ sí seng irú nǹkan wo ìsìn this contraction mo ti ṣe paper kan tẹ́mi improve nǹkan ṣe from contraction to àwọn low projection contraction yìí ni method táwọn yẹn lò nù paper yẹn àwa change ẹ̀ sí subgradient I'm going to add it to this thing now nǹkan tẹ́ máa wo ti pọ̀ paper tẹ́ máa wo fi pọ̀ so ẹ máa rí nǹkan tí mo sọ táwọn yẹn ṣe paper yẹn gangan táwọn ṣe nìyí àṣé mo save it síbí I think it's this only the same contraction projection contraction náà lè lè báyìí sìn lè lè náà ṣe ń sìn so àwọn ṣe alternating inertia náà ṣe síbẹ̀ so projection contraction yẹn náà ni projection pẹ̀lú ọ̀rẹ́ so yìí ló fi ń jẹ́ contraction méjì ilé àtẹlé ló fi ń jẹ́ so this is projection contraction so níbí náà òun náà ni step méjèèjì yẹn ni this guy and this guy so projection contraction òun náà lò and instead of using self-adaptive line search náà lóyún nǹkan tó pè ní line search ní 6 yìí ní line search so another thing that to improve eléyìí instead of using this guy a máa lo self-adaptive and instead of using contraction a máa change it sí subgradient ẹ wá wo ti wá ń sìn ẹ máa rí pé subgradient làwọn lò báyìí but paper tá n try láti improve àwọn lo projection contraction so the same thing irú eléyìí sìn bó ń ṣe lo projection contraction sìn àwa lè change ẹ̀ sí subgradient bá a ṣe ṣe nínú paper yìí ṣó ń clear báyìí then double inertia method tó lè làwa náà fẹ́ add in sìn and also a máa wá fi fixed point síbi tẹ́lẹ̀ báwọn lè ṣe lo fixed point in sìn and so which means pé the only thing we just need to do is add this double inertia to this step ó tán kàkàn add so double inertia sí kíní lásán ní nǹkan tá a fẹ́ ṣe double inertia tó wà níbí a fẹ́ add sí method àwọn ilé ìlú ń báyìí that's what we just want to do so we might change iṣẹ́ entirely from what they have done now to the combination of this paper here and this paper here just add the double inertia from here to this paper nǹkan tá a fẹ́ ṣe ń sìn yẹn so clear.
Yes. Clear.
So the two papers are already with you, this guy and this guy. But I can add this since this. So this is it. And step size too, I'm already. With step size, like a perfect step size, it's here as well. 1B now. So everything you need is here. The only thing is just how do they work? Need to do now. And another extra step máa wá gun eléyìí instead of máa jẹ́ tó fi máa end sí bí báyìí sìn extra step tí ń bọ̀ bí báyìí sìn so but ẹ lọ work out kí everybody kọ algorithm then let me check let me see who is very close to the correct thing so and we take it from there next class. Any question on the assignment?
Okay.
Yeah,
Mo ní kí ẹ bá wa recap sir. Paper FPP yìí báyìí òun ni a fẹ́ àdọ́gbù náà ṣe àmàrí.
òun la fẹ́ àdọ́gbù inertia wọn double inertia rè láti bí báyìí.
Okay sir.
So if you look at that thing, what do you see here? UN and WN. So this is a converse combination of the UN and ZN here. UN and ZN, UN and okay, UN, only UN came here, but WN Lutimbo, last B. You can see WN, until the WN law DB, the only place see EBY and UN Sheshawajadi. So we see UN Sheshawajadi here. So, but mi ò ní sọ ohun tó máa ṣẹlẹ̀ níbí. I don't want to mention it here. So, ẹ lọ ṣe náà kí n wo nǹkan tẹ́ máa come up with. Ẹ lọ kọ algorithm títí. So just add these two. Add this step now. Just add the step yìí nìkan la fẹ́ add síbí báyìí.
Okay.
So whatever way they have worked that step out nínú paper yẹn sẹ́yìn, nígbà tí ẹ bá fẹ́ máa proof tọ̀dọ̀ yín, òun lẹ́ máa lò. Gbogbo wọn wá ṣe deal pẹ̀lú UN and WN yìí, you're going to find them in this paper already. So every other thing fún àwọn ilé tó ti wà lé already náà, ilé already ti wà nínú paper ilé. Gbogbo ilé ti already wà nínú paper yìí ní títẹ̀, so no kò sí problem pẹ̀lú yẹn. So the only thing that you're bringing in is these two that I've just added to this one. So that's all.
So our FM plus one náà ó máa remain the same nínú FAP yẹn.
Lọ ṣe títí tí ẹja agbọn tí wọ́n bá mú jáde nípa gbogbo títí ẹ̀ wá.
All right, sir.
All right, so.
Any question, sir? Any only question?
Me, because I'm much my local.
Okay. Who must have some call?
Kò sí question, màá ṣe èmi náà lọ check.
Okay. So that was coming to the end of the class today. So pé kò gbà á pé ní nǹkan tó pẹ́ láti review paper ti bí yẹn.
Yes, once at any background there.
Exactly. So eléyìí ṣe review méjèèjì, review wọn papọ̀ again, then ló fi máa ràn yín lọ́wọ́. And another thing is it's not even about reviewing it again. Work them out. Tẹ́ bá ṣe tẹ́ ń ṣe step by step náà. So máa tún jẹ́ kẹ́ wà used more. Like all these things now, there are some analysis here that you have to look at those things. Báwo ni you get kíní kan, báwo ni you get kíní kan. It's all about pé wàá kàn sáré sọ kékeré báyìí sọ yẹn. Ó máa ní àwọn iṣẹ́ kan tẹ́ máa ṣe ń bẹ̀. Like this thing now, how did you arrive at this? Kino loan combine. So those things are very, very key. So, but first, let's see what you can do for the algorithm. I think I should add this one too. Yeah, they really help you come by one or two things. Maybe you can do one or two things. So what those two, our major lab was to send the most important. But it's not bad if you have this one too. Why need that to work on? You go there and check. Okay. So we'll meet next time.
All right.
All right, thank you.
Jazakumullah khairan.
Ó dọ̀la. Bá mi kí gbogbo ilé yín.
Àgbọ̀.